the idea of partial sums is very commonly used to try to approximate what an infinite series, or the value of an infinite series. And actually it brings us to a point where we can actually, in some circumstances, based on a partial sum, make a determination of what the infinite series actually sums to. So let's play around with this example. Suppose we have a sequence such that an equals 1/2 all raised to the n. Then the partial sum of this sequence is given by, and let's take this piece by piece here. We typically use a capital letter S to represent a partial sum. So S1 is actually going to equal 1/2 to the first. S2 will equal 1/2 to the first plus 1/2 squared, which is what, 1/2 plus 1/4, which is 3/4. S3 will equal 1/2 to the first plus 1/2 squared. Oops, this is supposed to be to the first. Plus 1/2 cubed, which is equal to 1/2 plus 1/4 plus 1/8, which is equal to, let's see, 1 plus 2 plus 4 over 8, which is 7/8. Now I want to go back just briefly here and see this value right here is actually A1. This value, or actually both of these, is going to be A1 plus A2. Here what we're actually dealing with is A1 plus A2 plus A3. So this partial sum, I go dot dot dot, Sn is going to equal 1 over 2 to the n plus Sn minus 1, or Sn minus 1 was the sum of everything that came prior to it. Or another way I can look at this is this could be equal to A1 plus A2 plus yada 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 out to An. This is saying the exact same thing that this is saying. Now we can actually think about this for a moment. This particular sequence we can think about for a moment geometrically. Let's just suppose that this is a box and the sides equal 1. So the area of the box is equal to 1. Well, first, if I take half this box, this is S1. Then I added to that half of the other half, which was 1/4. So S2 was 1/2 plus 1/4. Then S3 was everything prior plus 1/2 of this last piece, which is 1/8. So the S3 is 1/2 plus 1/4 plus 1/8. S4 would be 1/2 plus 1/4 plus 1/8 plus half of what's left, which is 1/16. See, S5 would be yada 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 yada. And you see what's going on is every time what's happening is I'm taking 1/2 of what's left over and I'm adding it up. So conceivably, in the limit, I'm going to add up, I'm going to be adding almost essentially nothing. So when I add all of these pieces up, I should get the sum of the ANs equals 1. Now, shorthand notation, very commonly we will write the sum like this, without any type of subscripts. And this is simply understood to mean the sum 1 equals, or n equals 1 to infinity. So if this whole area equals 1, I should add up all these little pieces and get infinitely close to 1. Clearly, I can't add up all these infinite pieces and get something bigger than 1. We can also think about this in terms of a graph to help you visualize perhaps a little bit better. Let's see, here's 1, 2, 3, 4, 5. And let's say up here is a line y equals 1. Well, when n was 1, I was at 1/2. When n is 2, I'm talking about the partial sums now, I was at 3/4. When n is 3, I was at 7/8. And I think you see, if you keep going, what's happening is I'm cutting this distance in half every time. Asymptotically, I'm approaching the line y = 0. And remember that each of these values represents the sum. So Sn equals the sum, the value here on the y-axis, which we said was the sum. N equals 1. Yeah, I need to change the subscript real quick. I'm going to say I equals 1 to n of 1/2 to the I. Now, if n equals 3, I goes from 1 to 3, so I have a half plus a fourth plus an eighth. So this would represent the partial sequence, a partial sum of the sequence 1/2 raised to the n. Whether you think about it geometrically in terms of a box, or we think of it graphically in terms of what the value of Sn is, either way, I think it's pretty clear that this thing will actually converge to 1.